Hi all, Claire here again, and I fixed that pesky Zoom issue, I think. Yes, I fixed it. Okay, brilliant. So I'm going to just take you through what my dissertation was, because that's a piece of the dialogue problem that I have already solved, and I also think showing the results and talking about the results would be helpful. Before I go into the actual results and what I achieved and what I found, I should really stress that there's a lot of throwaway when you do research. About 90% of your work you throw to the side. So when you do R&D, a lot of times you have to go down dead ends. One particular dead end I pursued for months with this was semantic networks and looking at making the current semantic research that's going into understanding language into my research, and got really bogged down in it. And I eventually dug myself out of that hole because I realized it wasn't really relevant, and because I could define, I already had definitions of objects in the game world by their components and their behaviors, and there were already a series of semantics there for me to use. They just weren't linguistic semantics, and as long as I worked with the knowledge model that already existed, the knowledge representations that existed in the game, and made sure whatever the game did was augmented correctly to allow discussion, then the interpretation to language could actually be done during the formulation of the response, and the whole semantic mess could be removed from the object model. And so anyway, that's the kind of thing that you can spend a lot of time on straight away. So this video might be a bit longer than the others, but it's the only nice way to really dig through this as an overview. I may dive in deeper into topics at another time. Okay, so basically there was the research phase, which was quite pretty intense. After I'd done all that research, we then looked at 3 prototypes that had 3 specific purposes. The first was an XNA prototype. The reason for this was mostly to look at what I call the atomic data structure, and if we could come up with a data model or a representation that would work with existing game data models that you see in commercial games, or could augment those models in a fashion that would allow for multiple representations of data. I'll get to that in a second. The second prototype was an XML query prototype. It was originally meant to be part of the original XNA prototype, and then I thought about doing it in other ways, but at the end I realized there was already an existing standard that I could use, and I could formulate my response on in a very high level way, and if it was done this way, then it would be easier to drill down and implement for people in their own systems, because it was fairly generic and it wasn't tied in too much to proprietary work that I had done. Finally, there was the Python parser, which was to prove the second degree authorship from a rules dictionary, which was the purpose of this entire dissertation. As I say, the problem I was trying to solve was prove second degree authorship, and that the data you created through second degree authorship or in the game world could be queried and responded to. So to run through those, the XNA prototype was to define the data models and investigate the atomic data model structure. Nothing too thrilling there, but was very thrilling. The query prototype to establish a formulated response structure, which could be built upon and expanded upon, and the Python parsing system, which was simply to prove second degree authorship. So I'll run through those 3. So the first thing was the XNA prototype. Now, one of the reasons I specifically chose to do this in XNA was C# gave me a bit more data flexibility with some of the more modern language features it has over, say, C or C++, which are the industry standard. However, it's close enough to those that any work done here could be fairly easily adapted, whereas say Python is a bit more out there. So let's go through this. I'm just refreshing my memory, blah 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 blah, dialog trees, I've already talked about all those, and oh yeah, nice little pictures. I'm going to be making my dissertation, I'm posting it up with this video. Post solution, blah 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 blah. Okay, here it is. Okay, so the atomic data model, here we go. Right, so the big problem with data is that it can, when you first try talk about how does an agent understand what happens or a situation that occurs, or it's very easy to get messed up, and a lot of good software engineers and a lot of good game programmers will now tell you if you get the data right, you've solved half the problem, you've optimized most of the stuff you need to optimize, because most of your slowdown in games is actually I/O. So there's a lot of work in data, and there's a lot of denormalization that goes on to speed things up, and there's a lot of packing structs. There's a lot of stuff we do, but it's quite a tricky problem, and there was quite a bit of research that I spent on this. The model I came up with is one possible model. It was more to prove its viability than to come up with a definitive solution, because I don't think there is a definitive solution because of the variety of games that could, or the variety of scenarios this could be implemented in with. However, I think would fit most, say, first-person shooters or structures like that. Okay, so the biggest challenge with data is we need to decouple it. Now, coupling basically means that data is intertwined in such a way that it's very hard to remove. So it's connected, it's a whole piece. Now, if we decouple the data into atomic components, now that sounds very fancy, but all it actually means is that each piece is self-standing, each piece is its own piece. Okay, so I've got a pretty picture here which is in the dissertation, which I'll, as I say, post up. So you've got the agent. Now the agent container is basically any character or entity in the game. As I said, we use agent to refer to any intelligence in the game. So you've got the agent, and you've got its loosely contained knowledge. I say loosely contained because in reality you're most probably going to want to store this away from the agent, just for flexibility. And you've got some core functionality like what does the person have in terms of objects, what objects are in the room the person has, and get the actions of the person that they have performed. You know, a list of actions that they have performed. Okay, I won't go through this in loads of detail because, as I say, I'm going to post it up. Basically, the big challenge for me, and this really helped with working on that Alliance project I was telling you about, was finding a way to represent this data in a fashion that could be broken down. So what I did is I broke things down into knowledge blocks, if you will. So you've got people, you've got objects, you've got location, and you've got time. Okay. Now let's take an event like a Quake event that everyone can relate to. I'm running along with a rocket launcher and I shoot at someone. Okay, so player A shoots at player B with a rocket launcher, and explodes on their feet, and near their feet, and it deals damage to them. So now the first event there could be described as player A firing the rocket. Now this could be broken up into discrete parts. There is the visual component of identifying player A has fired a rocket. There's the auditory component which identifies that there is a rocket that's been launched in this direction. Okay, and then that's kind of that. and then the pieces of information is who's fired it, where it was fired from, what was fired. Okay, so you see that you've got the granularity of the sensors there, like how is this information broken up, and then you've got the pieces of information you can convey with this event. And now it's important to realize that that is a discrete event, firing the rocket. A secondary thing that could be observed would be the rocket in travel. However, it again comes down to the fidelity of the data you want to actually parse. Do you want to parse whether the rocket was seen in travel or whatever? And then the third event that you can clearly distinguish, or the second event if you ignore the rocket's motion, is the explosion. In this case, the only information that's present is a rocket exploded, its direction from which it came, possibly. Did you see the explosion? Who was hurt by the explosion? And when you start breaking events down into these like discrete elements, and you start building up these massive tables of events in a timeline, and it starts breaking down really nicely. In this example, in my example, I've basically broken down a person into a list of status qualities at a given. Okay, let me back up. Okay, so what you need to do is you need to break this data down into something that has non-time sensitive and time sensitive. And the time sensitive stuff you need to be able to pin down to an exact time. It generally helps in your data model. So what I did is I made this loose model that's called atomic data, its time, and what the data is. So for example, a person, like say a Quake player, would have a list of statuses, and these statuses would have a dictionary of times and what they are. So for instance, a status could be health, and health could be 100% and then drop down to 80% and then come back up to 90%. But now the important thing about a status, or about those rocket events I talked about, is if you as a player, a third player, see the explosion mark on the floor, you know that sometime between the last time you saw this position and now, a rocket has exploded. So you can assign a time frame to that explosion, and you can ascertain some of the data of the event, and you also have a degree of certainty towards that as well. Likewise, if you were in the next room and you heard the rocket explode, then you can mark down that auditory event, and you can give it a certainty and a timestamp, if you will. And it's this ability to give partial information that the agent knows is partial information or is incomplete or has a degree of error, so they are able to assign trust, which is the key component of the data model. And also the ability to be able to genericize everything, because you don't want these couplings between arbitrary things, which is why I said this huge status thing, which is not that efficient, to be fair. And if I was doing a high performance game and the dialogue was not directly related to the performance, like say I was to take Quake and I was to put a chatbot in Quake, but the chatbot only talked in the lobby, then what I'd most probably do is I'd fire off this data into a very compressed format that was very proprietary and not readable. And then near the end of the session, as part of my cleanup, I'd take that data and I'd denormalize it and decouple it. Denormalize it basically means I'd break it into more readable chunks, more parsable chunks. So I'm trading memory for computation time later. So when I actually come down to the dialogue, I don't have to do these obscure calculations. So anyway, if you get to this position where an agent can talk about data in a very atomic sense, again, I'm throwing this word around, but literally all it means is that they don't need to have loads of knowledge. Like, for instance, if and I'll come to this in the third part when I'm talking about the authorship program, the Python program, if I'm talking about a game, hair color, for instance, doesn't matter in the game. But then one of the designers decides, let's add hair color as a quality into the game. And the moment you add hair quality into the lexicon of the game, into the dictionary of definitions the game has, you need to be able to talk about it. But you don't want to have to rewrite your dialogue system or rewrite your knowledge system to understand what is hair. So your data model has to be genericized and have a series of qualities and attributes that can define hair with and possibly expand upon that definition using descriptors or whatnot. So that's the important part, if I made sense there. So we can talk about an event in a game like a player shooting a rocket at another player, and then if I'm a witness of this event, we can break it down into various pieces and bobs. As I say, if you're interested in the actual details, my dissertation is a lot more concise and has pictures, which always helps. But yeah, it's there, and you see how I kind of struggle through defining it, and this is only like the bare minimum. I actually struggle really badly to break this down. It's been bouncing around my head a long time, as I say. Lots of research goes into it. So anyway, once we had done that, and we had got the data model defined, and we had proven with the XNA prototype, because what the XNA prototype basically did is it randomly spammed information into the data model, and then using an early form of the query system, which, as I said, I then moved into a second prototype, I was able to query this data, and I was able to prove that, hey, we can have a certainty of data, and we can talk about data without necessarily knowing about it. Okay, so here we go, query and response. So the second prototype I worked on didn't actually require much programming. It required a hell of a lot of research, and it required a hell of a lot of failed programming. But what I had, once I had these atomic events, is everything could be described as an event, a person, a place, an item, and a person or a place could have an owner, if that makes sense. Yes, a person or a place. No, a person or a place could be an owner. Sorry, yes, a person or a place could be an owner, because they could be a location where an item is, or a location that could own something, if you know what I mean. And all of these are a poppable context. Okay, that'll make sense in a bit. And then what these can contain is they can contain atomic or persistent data. So data that is time sensitive or data that is not time sensitive. Right, because like for instance a status such as a person's name is not going to change in your game unless your game has very confusing name change conditions. You know, so it kind of makes sense. So then what I did is I stumbled across XML, and I'd really done quite a bit with XML, and I remembered this thing called XPath, which is a method for querying XML. And now if you can construct your query, like get away from linguistics, right, and think about this data that's decoupled, but this data has relationships. And I thought, well, how can I build a query on this data that is working with all these different statuses? So let's take an example that's from my dissertation here. The natural language example here is, what is the prefix nationality? Okay. Now the query is actually, well, you could say, what is John's nationality? Query is query. Okay, so here we go. Yeah, query. Leaf node John. Leaf node nation. Leaf node unknown. Right, you see what it is there? And then the agent can use this to parse their the thing and go, okay, I've hit an unknown, what can I return? And if there's a single known value, return a single known value. If there's not, return a query for more information. So like a very open-ended query could be query person unknown. Now, I have loads of responses to that, and the natural language equivalent would be, who do you know? And again, I'm talking about the very stale back and forth here, because that's where you kind of have to start. It's quite easy to add. It's quite easy to add detail later. So I can go query locate. Also, here's an example. Who was in the inn when the prefect sent the note to the captain? Now, the prefect sent the note to a captain is an identifiable event which I can place in the timeline, right? So I can refer to it by an event code, because I have knowledge of that and you have knowledge of that, and we know what we're talking about. So I can go query location pub event 5, say person unknown, and I will return say 3 leaf nodes there into that response. It sounds, as I say, it sounds very boring, but what you can actually get to is you can get to a situation where you can go, you can construct quite complex trees, and then fill them using this unknown. And the way language works is it's very context sensitive, and this tree really lent to that, because it meant that you can just each time add a single node onto the bottom of the tree, and based on what we've previously added to this tree, we know the context of our conversation. And another problem that was having was this infinite memory problem, and the joy of the data being atomic is the moment there's two items of the same type in the tree which are parented at some degree. So let's say I've got location, person, event, location, and the location was a response or a query. Then I can pop off the top location without any loss of context, really. I mean, you do lose some context. Language is a very tricky thing, but I found it a fairly solid system that I could navigate the data I had without losing much. As I say, it doesn't feel very natural, but it doesn't have to. As I've said before, the input problem and the output problem aren't what we're trying to solve, and taking natural language and breaking it into that, or taking some kind of game dialogue system and breaking it into that, now it's a parsable problem, it's a solvable problem, because you know the data format you're going to. It's like when you're working on compilers, and once you know what the abstract syntax tree you're going to is, then you can kind of go there and you've kind of solved most of the problem. Okay, so I'm very aware of the time, so I'll go forward here. And finally, the third part of the prototype was to prove the second degree authorship, because what's the point of filling a data model with random noise and then querying it? Can this hold meaningful data? And this got very interesting. So what I did for this is, first of all, I made a fake conversation with a single character between another character I drew up a reference scenario called Murder in the Mines, which I'll link to as well. And in this reference scenario, I came up with a bunch of stuff that had happened, roughly. And I, as a test, because I had a real hard time tracking down good solid production times on dialogue trees or just general dialogue trees. So as a example and test, I timed how long, and I constructed a sample, very simple dialogue tree between one of the characters, the barkeep, and the player character, and the various responses they would have. And I did it in HTML, and I'll again link it with this video. and sort of went through that concept. And it took a fair chunk of time, as I knew it would. And then with the second degree authorship, what I did is I took the same scenario and I took a single room at the pub, which was a fairly crowded room, I should add, and I came up with a set of rules. So how this works, right? Okay. I came up with a set of rules and definitions that allowed, through a very simple seed, us to author the situation. Now, what am I talking about with second degree authorship? I realised I might have jumped the gun there. First degree authorship is me writing a sentence like, the lazy brown fox jumped over the fence. Right? Second degree authorship. But that's first degree authorship, sorry, because it's first degree. Now, second degree authorship would be, say you're standing on stage and I tell them how emotional you are, or your father's just been killed, or your lover has left you and run off them, and I give the actor a rough guideline, and then that person fills it out with their own words, and that's second degree authorship. I don't have to fill in all the blanks. It's very similar to what a lot of playwrights do, for instance, for scenery. You know, what you'll do as a screenwriter or as a playwright is you'll write interior old monastery, or broken down building or whatever, and in a location, the sets people, they do all this work and they set it up and blah 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 blah. That works really well with games, because that's kind of how like role-playing games goes. I tend to seed a scene with information and the players fill in all the bits. And content generation kind of proves we can do this for environments and blah 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 blah. It's a developing field, but I needed to prove, can we do this for the social interactions and the kind of the status and the data model I was talking about. Because I'm, as I say, convinced we can do it for, say, the character and the scene setting and whatnot. It takes some work, but I do think it can. So anyway, how do we go about this? Well, it's quite simple. The system is broken into. Here we go. So I'm explaining a lot of stuff here. As I say, I'm just trying to break it down for you all. Right. Okay, verbs, place, location, data format, common elements, event-driven, suitable data, authored skeleton. Okay, here we go. Now, I might as well just open the code, because that makes more sense. At least to me it would quickly just bring me to how do I explain this to you all. Okay. So, what I do is I have a dictionary. The game dictionary defines the global contents of statuses and their quality. So what I did as valid status options. Now again, these would vary game to game. So I said you could have an enumerated list, you could have a numeric range, and you could have a Gaussian range as your definitions. Now, it sounds a bit strange, but I'll explain in a bit. So, for instance, the global status of height, how tall a character could be, was between 1.2 and 2.4. Whereas what nationality were they? They could be red, green, or blue. And then status hair color could be red, ginger, strawberry, blonde, brunette. Okay, so this establishes what the status is, and it establishes numerated range, or it establishes basically a set space of which this can exist in. And then once you've got these global rules, you can have modifiers. These modifiers are based on other qualities. So For instance, let's say this murder in the mine set was set in the Red Nation, and let's say you had the job of guard. Well, if you were guard here, then your nationality ipso facto has to be red, because, you know, red National Guard. So we have a modifier of, if your job is guard, your nationality is red. Okay, very, very explicit. Okay, in that, you know, there's only one option. These modifiers only operate in a signal direction. They imply equality. They do not. It's not a back and forth. However, we could also say that if your modifier, if your job is barman, miner, or a guard, then your gender is male. I know, sexist, but hey, it defines equalities. Likewise, with the scene that we had here, we could say if your modifier, if you were female, your job was immediately functionary in the prefix house, because that was the only valid place for the character to turn up. And your hairstyle was either short, curly, shoulder length, long, braided braids. So now what that did there, the second one, is it does a union of the global namespace, an intersection of the global namespace and the subnamespace, and we define what the current probability is. But now we can go a step further, because we can say, well, if your nationality is red, no, there's originality of this data, it's wonderful. But if your nationality is red, you've got a 80 chance of having red hair, a 12 chance of being ginger, a 3 chance of being strawberry blonde, a 3 of blonde, and 2 of brunette. And then sum those together and you do percentages and you get this wonderful probability thing. And you can stack these modifiers up and you get this wonderful space. It sounds really complicated, not all three at all, but it actually works out fairly well and it's fairly simple. And I actually got my friend who wasn't a programmer to write some of these rules, and they were very quick to grasp those. The one that's a bit more complicated, and threw them a bit, to be honest, was I could say the average height of a red nationality person is 1.7 with a normal deviation of 0.2. That's where the Gaussian one came in. Were very useful and very easy once you explain to someone that you're just talking, oh, well, you know, most people 1.7, there's a kind of a bell curve, and, you know, we're just doing that. And then you stack these up, and you get a list of rules. A list of statuses, which is your dictionary, and then a list of modifiers, which define, you know, what can happen. Other modifiers could be, instance, short, which means short modifies height to the bottom of its variance range. Simple enough. It's quite simple how it works in the code. So these modifiers allow you to be descriptive. So what we have is, let's describe the scene loosely that we're trying to generate. The tall barman is behind the bar cleaning a glass. There are several patrons are drinking. 4 guards are dicing in the corner. The bad English is there for a purpose. So what we know is location bar. Let's say that this is a handcrafted location. We're not generating it. Location bar. And we list the zones because I'm assuming the artists have broken down the scene into zones because it just works nicely and discreetly, and you don't want to actually work in grids or positions because it doesn't work for language and it shortens your data set quite a bit. So zones are counter, fireplace, tables, there's 8 of them, corner. So that's the location definition. And then a scene, drinking scene, location bar, person, and then I've got a definition where I've actually given the person a name in my script, Joe the barman, close script. He's a tall and he's a barman, so immediately I've given him a modifier to his height and I've given him a job, but then all the other statuses that we don't know, that we haven't set, will then be determined based on the dictionary and the mutators of tall and barman. So because he's a barman, we can determine a bunch of qualities and filter it all back. And then is, because we know he's currently got a verb, cleaning glass behind counter. So behind, it's fairly easy to have with each zone a few descriptive, I forget the word where you say whether something's above, below, behind, whatever, but those are fairly easy to map, and then you can say, oh, something's behind it or something is in front of it, and you can do those relative to the descriptive location of the player. It's fairly simple. So anyway, behind counter, and then we also define 4 people. They're all guards, and they are dicing in the corner. Again, giving a verb. Several people are drinking at table hash, because it's randomly associate these people to tables. And then we run through the scenario and we talk about how this actually can communicate. And then finally I go into imperfect knowledge and the Chinese whisper and the intelligent mutation of data. But yeah, so to summarize, because I know I've rambled there a bit, and I will be putting the link to the dissertation itself and the modular, but what we've basically done, and it doesn't sound like that exciting, but it's very easy to say these things. It's a lot harder to prove them, and that's what I kind of had to do. So what I did is I came up with an atomic data model that was decoupled, which allowed characters to describe events with a degree of certainty, as in they knew how certain they were about an event, and knowledge of how refined their knowledge was of the event, i.e. if there were missing pieces of information. And once this knowledge was in place, and I could prove that I could propagate this knowledge, and then I could prove I could alter a situation with knowledge. I could through second degree authorship reduce the cost of generating a scenario significantly. Finally, oh yes, and I know I'm going to get the haters now, so I'll tell you now. Yes, I do know what Lisp is. No, Lisp is not quite fit for the task that I'm talking about here. There are a few different qualities here. I did research it. Anyway, so after I've got second degree authorship, and after I've got this data model, I can also prove I can do a fairly high order but very machine parsable system of querying data, and data with context, which is also very important. The next step, which I never got to in the scope of this dissertation, which I was quite keen to get to, was the Chinese whispers and the propagation of data, because I felt I had done enough research. I was fairly close to the point where I could actually get agents automated in an automated fashion, talking to each other and trying to fill with 2 people with impartial knowledge, trying to fill in the blanks in a constructive fashion, and then say other people falsifying information or mutating their knowledge of the truth while communicating it intentionally in a fashion that they knew the consequence of. So, sounds all very heavy. As I say, if you read it, it's a fairly light read. It's fairly straightforward. I stress again, most of the time is spent throwing away stuff. I am going to make another video about explaining why I've chosen the research prototype I've chosen, because I thought about it a lot and I think I've got a solution there. So thank you for listening to Claire rambling on about her research project. Cheers.